So today I'm going to share with you this MAD book information. As you can see that the directory I have in here, I have each chapter, I have 12 chapters. For each chapter, I have a deck of slides. So together we have around 1,000 slides for this book. So I'm going to introduce this book to you. Then I'm going to zoom in on a specific chapter on chapter 11 called Analysis of the Design of Fractional Order Systems. And I'll go very quickly with you. This is only 100 slides, so very simple. But I actually want to focus is the MIMO fractional order. Okay, I'm going to tell you first. I'm going to show you this chapter 0, chapter 0 of this modeling, analysis, and design of control system in MATLAB and Simulink. So this is a World Scientific 2014 book. So the reason we use the MAD because Kevin Moore and I, we worked together for many years in Utah. And he had this vision about, for a control engineer, you have to go MAD, modeling, analysis, and design. So this is basically the flow chart, okay? So you do analysis, simulation, design, you have to have a model, okay? So this one, model development performance specifications, and whether you have desired performance. So you put all this, what do you want and what do you know, okay, into this iterative process. So you can see this is the iterative process. Then you have this model for control that you implement, you have a new system. So that is the picture. So modeling, analysis, and design. And finally, you need to put this one into action. So this HIL stands for hardware in the loop implementation. That's an early stage of real-time simulation, including the physical plant in the loop. So we call hardware in the loop. So we have a book service website. It's called MADBook /MADBook under our lab's website. Okay. So this is our lab web page looks like. So you go there, you can download a lot of things, including the slides, even solution menus, and so on and so forth. Okay, and the slides in the bilingual Chinese and the English, so you can teach this course in both languages. So there are three important components in the book. One is you need to learn the language to implement. Okay. So this is Confucius said, the mechanic who wishes to do his work well must first sharpen his tools. What are our tools today? MATLAB and Simulink. Okay. So then modeling analysis of control systems. Okay. And we can also using Simulink to deal with nonlinear systems. Okay. And then we can learn and practice various design approaches. D, okay, D. Okay, so yeah, that's the controller design part, shows all your smart ideas to make the system to behave as we wish. So we have a few other books to focus on, like math problems, like Simulink techniques. And we have all the menus for all the math works are now, all the toolbox are now online, you can learn. Okay. So why use MATLAB? I don't think this is a question anymore. So it's called, in fact, it's an industry standard as well as standard for academia. Okay, both. Okay. So I'm not going to go through this justification about program writing, data structure, linear algebra, and stuff like that. So you can see there's a running docs in here. There's a small one. That means you click this guy, then all the code will go to a buffer. It's like you copy. Then you paste into MATLAB, okay? It will show up. Let me do an experiment for you. So you can, so what you see is what you get, okay? So this is the MATLAB starting. A little bit slow, but it's already fast enough. So you can see I have nothing here. Now I'm going to my slide. Okay, so this is my slide. Just you take a look of this one. I go from here. I say enable editing and enable content. Just say full screen. So so you can see this is to plot this type of curve. Okay, this type of curve. Okay, this type of curve. So then what I'm going to do is to click this guy. Click. Okay. What happened in the background is to have that code on the slide. I do Control V, so you will see this is drawing a picture like that. So that's the a good idea about not having the figure cut paste on this one. Okay. So I don't want to put a figure here. I want you to click the animal, then you paste, you will see what the MATLAB says. Okay, it's very interesting. Yeah. So if you have an implicit function, okay, so like this, so equals 0, and how you plot the fx. So there's an easy plot by doing this. So I click this one, and you will see there's another nice Control V here. So what are you going to see is this one. Oh, okay. So these are like contour plots. Okay. So you do a lot of symbolic computation as well. Okay. You can declare a T is a symbol. Okay. It's a symbol. Do the symbolic computation. Symbolic computation like this. Then you can do Laplace transform of it, or even you can do many other things. Okay. So this is a block diagram of traditional DC motor control, and you can define all these as the symbols, and you can come out symbolic feedback system. If you don't have this function, and then you should download the code from the service website. It's already there. And for nonlinear system, you can do Simulink. So that's all. I gave you a preview. So outline of structure of the book here is the first part 1 is fundamentals, like 3 chapters talking about how to use MATLAB survival techniques and the scientific computing, some of the basic ideas. So these are 3 chapters, okay. First chapter on the introduction, why we need it, then MATLAB fundamentals, then scientific computing about linear algebra, ordinary differential equation optimization, and Laplace transforms, how to do it with MATLAB. Part 2 will be a modeling and analysis. So like how to describe a linear time invariant system, how to analyze it, and how to modeling analysis some nonlinear systems. Linear system modeling, okay, and how to do a conversion of different models, the transfer functions, state space, and so on and so forth. I even talk about system identification, given data, what's your model, okay? So it's pretty complete. This is a good book. So chapter 5 is analysis of linear system, modeling simulation for nonlinear systems, okay? So then part 3 is regarding design. So we have 5 chapters talking about classic control, PID. So these are the designs. Robust control, adaptive intelligent control. Today we are going to go through basics of fractional order control, especially in the MIMO case. Okay, MIMO case. It is not very hard to put your hands on this, so don't think this is hard. Okay. So the part 4 is the hardware in a loop simulating, how to simulate to control actual plants. And we do this one in the hardware in the loop simulation in our mechatronics course. to bridge the theory controls practice theory gap. Okay. So these are the information. So about this book. So now I'm going to go through chapter 11. From the chapter 11, so this is the cover page. Chapter 11 is regarding analysis and design of fractional order system. I'm assuming that majority of my students, our MATLAB members, they already know fractional order calculus, fractional order systems. But for many of you online, you probably never heard about fractional order system. What does that mean? And what are the tools we can use to solve this fractional order system problems, to do MAD, modeling, analysis, and design, okay? How MATLAB can recognize a fractional order system, okay? Okay. So first of all, the fractional is a misuse of terminology. It actually can be any number, real number. So the correct word should be non-integer order, okay? Not just fraction. It can be real number. It can even be complex numbers, okay? So main topic in this chapter is basically some basic computation, giving a function, how you can do a computation of fractional derivative, fractional integral, and how you do analytic solutions and numeric solutions for different fractional order differential equations. What is the fractional order transfer function? So this FOTF is already widely used, and it has gained a worldwide popularity. A lot of people are using this. So regarding those technical details, like how to realize fractional order system, how to do block diagram to simulate that, how to make optimization of fractional order PID control designs. Probably we should not go to that details. I'll flash you through some of the slides. You can see I have 105 slides, and I have how many hours? I got the maximum 15 minutes, okay? So I'm going to go to very quickly. So this is Isaac Newton invented this notation, differentiation, by using primes or dots. Leibniz invented the bracket, differentiation bracket and integration sign. Also, this is invented by Leibniz. So because of that n notation, then somebody else can ask, oh, what if the n is not an integer? That was asked by L'Hopital, who invented L'Hopital rule to do the limits, remember? So this is equal Polumni. L'Hopital asked Leibniz, what if n is half? So actually Leibniz gave a half order derivative of t, which is 1695, is considered as the birth of fractional calculus. But initially it is indeed a fraction here, but now everybody knows. 1960, and Manabi published papers on fractional order control. Igor Polumny 99 and published the fractional order PID, where I and the D terms are fractional order. So it's a 1999 IEEE transaction automatic control. It's widely cited. So this is a Cauchy integral form, Gromov-Litten nickel form. So this is just simply like our finite difference type of definition, okay? And interestingly, all the coefficients can be recursively expanded. And so that's very good for numerical implementation. So when h is small enough, then the accuracy is the first order. And today, of course, people invent many other schemes that is O of h to the power of something higher order. So Riemann-Liouville integral definition is based on this form, okay? So then this is considered as alpha is less than 1, then this is 1 over t minus tau and 1 minus alpha. Then it's a convolution kernel with this f of t, okay? So that's the fractional, that's the Riemann-Liouville's fractional integral definition. Then differentiation is just do integer order differentiation over the fractional order integration. Then you get fractional order differentiation. So then looks very complicated. That's easy, okay? That's easy. Caputo's definition is you have an integer order differentiation inside first, then do convolution. But here you have a convolution first, then you do convolution first, then you do a differentiation. So it's a swap to the sequence here. So in many cases they are similar, but for initial value of f of t is non-zero, then you need to be careful about this non-zero initial condition. So Riemann-Liouville and Caputo, they are different. So then for this initial condition is a constant, Riemann-Liouville will give you a non-zero, okay, it's not zero. So therefore, Caputo and Riemann-Liouville, they have this missing term here. Okay, but if f of t zero is 0, then they are all equivalent. But if it is not, you must be very careful. But integration, they are the same. Okay. So these are the linearity. So I cannot do this slower. So how do you compute? So for example, Gromov-Litvinenko fractional differentiation. Okay. GL, F, if. So you given a data signal in Y array, you have time, okay, evenly distributed. You have gamma is your order, so you can just do this. Okay. And now there are some examples you can try, but in the interest of time, so IO means integer order characters. So you'll see this is for sine t plus 1 and how so maybe we'll take a look at this one. I think it's not working. It's because I didn't enable. Should have worked. Okay, I think we should skip this part. So we have lots of examples. You can run it. Oh, this actually should work. It probably already worked. I didn't notice. So let's try the sine t and having a order from 0 to 1 and step. So you can see a very nice. So probably it's already in the. We'll see. Yeah, it's already in. Okay. So you are going to see that this is a very interesting. Yeah. So you can play this one later. I'm going to upload all the slides in a CAT course. Okay. So Caputo, you have the same. So you have this L is the length. Okay. So Y0 and alpha and T and Y is your array of signals. So you can do the plots and see the differences. So then we have to introduce MATLAB function. Is a generalization of exponential function like this. So when you have different alpha, when alpha is 1, then it is an exponential function. Okay, so that is called MATLAB function in 1 parameter. There are MATLAB function in 2 parameters. So alpha plus beta, and when beta is 1, it's the same as 1 parameter. And these are the implementation you can play. Laplace transform. So for fractional order Caputo derivative, when you do a Laplace transform, you will s to the power of gamma. When gamma is 1, this is s. So we learned this one before. And remember, here are all the integer order initial conditions, okay? So then we come to the fractional order differential equation. So that is this form. So if we how to simulate this one, you have input, you have differential equation here. You can do this one by putting a ground Leibniz-Coff definition and discretize it. You will be able to solve it. So actually, the code is like this. So you have A, eta, B, gamma, U. U is the input. Okay. Come back to here. So your A is array of A1 and AN, N1, eta1 and eta2 and eta n. Okay. So this is an array of eta. So these are the realization. So Professor Xue wrote the code very beautifully. Okay. So giving the example like linear fractional order differential equation. So you have all these things, and you also have this. So you can solve it. Okay. So you can solve it basically. You can plot y and t. Okay. This is by the discretization of Grunwald-Leibniz-Coff discretization method. Okay. So, but anyway, so you have the codes to do this. Implementation wise, it will tell you how they did it. You should ignore all these details and learn how to solve your problem. So this is a Laplace transformation important formula that you have Laplace transform like this format, then it's corresponding to mid-tech level function in 3 parameters, alpha, beta, gamma. Okay, some special cases. Okay. All this you can get analytic impulse response. Okay, so you have many special cases. Okay, then there's something called commensurate order. You have a base order alpha. Others are just the integer order of multiples of this alpha. So this is called commensurate order, which you only have one alpha. Others are just multiples of that. So you can do some. This is called G lambda. This is actually called partial fraction expansion. Okay. You can get analytic solutions here. Okay. And you can discuss in the lambda domain where lambda is s to the power of alpha. Okay, so analytic solution, don't get bothered by this. Okay, you only care about the code that can work for it. So here is the thing. Okay, I'm going to finish in 5 minutes. So Professor Xue had a significant contribution by doing a programming. Remember, in MATLAB, we have a TF command, okay? TF command meaning you have, you can see here, you have a help TF, okay? So it's trying to input transfer function into your system, okay? Construct a transfer function or convert to transfer function. So you give a numerator coefficient, a denominator coefficient, then I can input my transfer function system into that. So here, Professor Xue said, we need something similar. So for the user, you only care about your coefficients A, your array of A, array of B coefficient, and your order NA. So let me show you an example. So these are how he realized this. Say, for example, okay, you have a system like this. You have a delay in here. So you have order in here. You have all coefficients. You have orders. So what you should do is you have A coefficient is 1.1, 1.9, 0.4. It is this one. Then you have a order of this one. So for first two vectors are for coefficient and order vectors. So 1.8, 0.5. Last one is s to the power of 0. So the numerator is 0.8 is coefficient, 2 is coefficient, then 1.2 is the order, 0 is the order here, and 0.5 is the delay. So that is the interface of FOTF. okay? So then you can overload the operators and enjoy it. So you generate something called G, it's called LTI object. With this one, as if you have the integer of the system. So you can just do it, do everything you want. So it's very similar to control system toolbox, as if you use a TF command, okay? So like you have multiply, plus, feedback, all this can be overloaded, okay? It's called operator overloading. Very beautiful. And you have two together, okay? G1, G2, you just as if it is integer order, okay? The only difference is when you first enter it. All others are implemented, so you don't know the details. If you want to learn the scale, you can do. So this is like a controller. You have a P, you have a I, you have D fraction order. So you can just write GC is a controller transfer function like this. Then you have G of S is a system like this. So you can cascade this together, do feedback control. So just do feedback, okay? So straightforward. Then you can do all the analysis like stability, norm, frequency domain, time domain, step response, and all the stuff can be done. So I'm going to go very quickly. So we also can do simulation because we actually here already did the fractional order derivative block. So we can put it in here. So this complicated system, okay, nonlinear, can be realized using this one. And you can download the code from our website. You don't have to redo this. It's already there. So people may be interested in say, oh, how I can tune these parameters, okay? And so there's a optimal fractional order PID design toolbox called FPID tune, okay? FPID tune. So it's called FPID tune. It will automatically give you a nice parameters you need. So you can do this one for direct PID control design. So at this point, you can use this. So you can see the limitations so far. We talk about SISO system. It's delay free. Okay. So we summarize everything. And so we have FOTF, and it's been around for 10 plus years, maybe 20 years. But I keep complaining to Professor Xue that, hey, we need a MIMO. Under my constant pressure, finally, he can do it. That is around 2015. He visited our UC Merced twice, actually, 2015 and maybe 2017. So then he finally he was able to tell me that finally I can do it. So that is our course material here. Actually, I already loaded it. It's here. So it's called newly extended. Oh, he was here in the November 18th in our UCM set. So, okay. So obviously, I just let you know for MIMO cases, the things is similar. Okay. So let me just go here. So this is a SISO. Okay. You already have heard. But what about I have a MIMO? Okay. MIMO is like this. Okay. So we can do the same thing as if for each one's size. So we see an example, okay? So this is how he designed. So say for example, I have a multivariable 2x2 system, okay? 2x2 system. So you enter G1 G2, G1 is here, it's at 1.5 is coefficient, 0.7 is coefficient, the order is 1.2, and this order is 0. So this 1 is here, okay? 0 is no delay, okay? So no delay, 0 is no delay, okay? No delay. So I think you can see that. So therefore, I want to write my G, just write G1 comma G2, and then line break G3 comma G3 comma G4. So if I have unit feedback, so just 2 by 2 unit I. So I get G1 is the feedback G, and I have the H. Okay, so then you have a closed loop system. Okay, so in general, we can deal with this type of model. Okay, this type of A, B, and this is delay, this is delay. So your alpha's order. Okay, alpha's order. So we can enter this. And sometimes you can also do a descriptor, a fractional order state space expression. So they put a E in here, and alpha actually can be a vector, meaning for different X component, X1, X2, you have the corresponding alpha 1, alpha 2. So it's pretty interesting. You can just put in A, B, C, D, alpha vector, and T, T is this delay, and E is this, okay? So of course, if E is not invertible, then the system is singular. E is invertible. X0 is your initial condition. So this is how he designed, and he's trying to have a 2 by 2 fractional system. You have a KP, a KD. So you can get closed loop automatically and find a common order. And if you find out 0.001 as a common order, then you end up with a very huge matrix. We have to use some ideas to reduce that. Well, so this is kind of extended state space model. So you have different alpha for different components and so on and so forth. So anyway, we have a lot of ways to input, and this can be done. Okay, this can be done. So you have original model like this, in matrix form. Okay, alpha, you have vector. So you also can do that. So that's modeling part, how you enter the model of a MIMO fractional order system in that. Then analysis, you have similar stability, state transition metrics, how to compute that, frequency time domain analysis, root locus, and other multivariable systems like a macros plot, like geoscoring bands, and like to see how they couple. Okay, so you have a MIMO system. I want to check the coupling strands, so whether we can have a diagonal dominance. Okay, a lot of topics can be done that. So I'm going to stop here, giving you some curiosity. You can explore the rest of the harmony slides. We still have about 60 slides like this. So this slide, these slides I'll upload to our system so you can enjoy and explore more with this. You don't have to do a lot of low level type of repetitive work. You can focus on your high level questions and start to do good research in MIMO fractional order systems. And of course, you can also do nonlinear systems because you have Simulink. Okay, so don't feel fractional order system is hard. We have the tool to help you. At least you can put your hands on it and play with it. All you need to do is click on this small, beautiful, lovely animal. Click, then you paste to the MATLAB and play with it and think about it. Okay. So with that, I'm going to stop my presentation, and let me check if you have any original questions you want to ask. Let me pause it.